Yeah, okay, sorry. I was a little out of sorts. I'm ready. Hopefully your notes are all ready to rock and roll. Shouldn't be hard. This is just actually a continuation of skills that you already possess. So the last 2 days were a setup for the next 2 days. Because one of the things that we have to do in one of our essential standards is working with radicals, and adding and subtracting radicals is where we want to be. And you can't add and subtract radicals until you understand how to manipulate individual radicals. So that's what the last couple days, and you'll practice some more today, because I know you still probably have a bunch of problems left on assignment 3, but assignment 4 and then assignment 5 and maybe assignment 6 are going to be kind of the target, and that is take a bunch of different radicals and add them together. All right, so that's where we're going today. Today is 1/12/23. That's a neat little date, 1/1/2/2/3, and we are adding and subtracting radicals. There will be no variables in today's radicals. Those will show up on Monday's assignment, where we'll basically kind of do what we're learning today, but the radicals will be like the assignment 3 with all the big X's and Y's and A's and B's and stuff inside of them. So for today, let's just talk first. This isn't an example on my note card, but let's just talk fundamentally first about the fact that you can or cannot add radicals together. So if I gave you like 5 roots of 2, and I said I wanted you to add 6 roots of 3, what would you get? 11. You'd actually, sorry, this is a terrible trick. Who does that? What kind of jerk starts their lesson with a trick question? You can't add these together. Radicals are like variables, not really, but in the sense that they determine whether or not terms are like terms. It would be kind of like me putting up here on the board and saying, what do you get when you add 5x to 6y? And you've been around me long enough to know that the answer is that's it. Like, that's the best I can do. So in the same way that x and y would make unlike terms, different types of radicals make unlike terms. So you cannot add those together. So if I put a problem like that, or if you get to the end of a problem and it looks like that, then you got to go, I'm done. I'm out. Like, this is the best that I can do. So today's lesson really more revolves around, like, how do we make radicals so that they're compatible with each other, right? So if I had something like 4 roots of 3 minus 10 roots of 3, I can do that now, right? Those radicals are the same. What would we get? You'd get -6 roots of 3. Right. And again, it's no different. Like, I know it's not the same exact situation, but like touchy-feely wise, it's the same as if I said to you, what's 4x minus 10x? You don't change the x's, right? They're still x's. You change the number of the x's that you have. So 4x's minus 10x's is -6, but they're still x's, right? So I know you've been combining like terms since you were like 12, so I don't mean to talk down to you, but that's the idea. Terms have to have the same things in order to be addable or subtractable. Okay, so of course you know where we're headed is what happens if we have radicals that aren't the same. Well, all hope is not lost. And so the idea is, can I take 2 unlike radicals and make them like? So we'll start with this, the square root of 54 minus 3 square roots of 6. So that first problem I gave you, it was what it was. Like, there was no work to do there. There was no end game to that. That was like, but this one, there's hope. So what do you suppose we ought to do or try to do? Right. So what we're going to do is we're going to manipulate radicals along the way to see if we can get them to play nice with each other. The square root of 54 is the square root of 9 times the square root of 6. You know, this will be a miserable few days if you still haven't figured out how to do that. And again, you can do this in the tree format because it's pretty not a big deal today, or you could do it in the just make one radical. So if you do the more tree looking thing, it would look like root times root. If you like it better just in one root, then you could think of it as just root 9 times 6 and continue to employ that jailbreak idea, right? So when the root of 9 pops out, like Bryn said a while ago, we get 3 root 6. And now if I say what's 3 root 6 minus 3 root 6, what looked like a hopeless situation is actually equal to 0. 3 x's minus 3 x's, what do you have left? Yeah, bupkis, nothing, 0. So if you say the answer is root 6, then you're implying that there's still one root of 6 left over, which of course there's not. 3 of something minus 3 of something equals a whole lot of nothing. All right. So let's try it with a different flavor of root. Let's a different index. You know what I mean when I say that. So let's say we had -2 times the cube root of 24 minus 2 times the cube root of 81. Again, at first glance, there's not a lot of hope for this problem because they're not the same, but maybe we can manipulate them. So since we've practiced our different types of roots, how can I break up a cube root of 24? Right, if it were a square root, I'd love 4 and 6, but 4 is trash in the world of cube roots. So I'm going to rewrite this. I'll do some color coding here. This left one, I'm going to rewrite as -2 times the cube root of 8 times 3. Right? And then I'll copy down my minus sign. And then this blue side, I'm going to rewrite as 2 times the cube root of what? What makes 81 that I actually care about? Say again? You're fine. 9 and 9 would be really cool because if we were in the land of square roots, but what is it? 27 times 3 makes 81. So I'm going to very purposely break this up into 27 times 3. Remember, when you jump root types, the list of numbers that you care about has to change when you jump. When you go from squares to cubes to fourth roots to fifth roots, your give a crap shifts. So yeah, and now we're going to have our good guys, bad guys. I'll switch colors here today because I already used up red. So just like before, I want to be consistent. That's a good guy, and that's a good guy. So when 8 busts out of jail, what does he become? 2. So I'm going to write -4 times the cube root of 3. I went ahead and just multiplied the new jailbreak by the pre-existing one. And when this 27 busts out of jail, what does he become? Good. So I'm going to write -6. And then you realize through some clever manipulation that you actually took a not so good situation and turned it into something where you can go, I can do this now. What's our final answer? Nice. Still good? Okay. What changes throughout today's assignment is, I mean, really the problems will get longer, like you'll see here in the next ones. And the roots will just continue to change flavor. So you'll have cube roots, and then maybe the next problem will have fourth roots, and eventually, probably Monday or Tuesday, when we really put it all together, we'll have problems that have cube roots and fourth roots. There'll be a mess, and then in addition to that, inside the roots, there'll also be like x squareds and y to the fifths and things like that. But it just, if you're here every day and working, and you complete assignments, and it's like that's how math is supposed to work. Is you never really feel math getting harder because you've done all the work along the way. So it's not bad. Let's do another couple. -3 times the cube root of 4 plus 3 times the cube root of 40 minus 6 times the cube root of 32. Completely terrible situation, but there is hope. So what do you notice? Anything a little, mm, yeah, first one's done. Like you can't, the cube root of 4 is unmanageable. Like we're not going anywhere with that. So that's going to be part of our answer. So I can just take this first one and just copy it down. Like there's literally nothing you can do with a cube root of 4. So you kind of know already, you're pretty smart, that where we're headed is maybe, just maybe, one of these other roots, as we work with it, will spit out another root of 4, or maybe they both will. I don't know. That we'll be able to play with the one that's in the beginning. So what do you think about this this second one here? 8 times 5, right? Good job switching gears there. So we're going to have plus, and then this one is going to be written now as 3 times the cube root of 8 times 5. And then I'm going to copy down my my minus sign, and then I've also got this, I'll underline this one in yellow. Inside the root, what can we do with the 32? 8 times 4, right? So we're going to have minus 6 times the cube root of 8 times 4. So that's the kind of worky setup step to all of this, and then from here you just acknowledge your jailbreaks. And so the 8's going to bust out of jail. What does he become? Right, a 2, which will find the 3 and make a 6. So in its current state, the problem says negative 3 times the cube root of 4. That was just the one we couldn't do anything with from the beginning, plus 6 cube roots of 5. And then we have another jailbreak, right? The numbers on this assignment are pretty reasonably sized, so I don't think you'll have any issues. So when 8 busts out, he creates another 2. So what will the number in front be? So minus 12 cube roots of 4. So once all the dust settles on this situation and you realize you've kind of, you've wrung that washcloth, you're not getting anything else out of it, then you just look at the situation and you take what you take. Like you get what you get, and you don't throw a fit. But you do see that there are a couple that can go together. And the order that you put them in, it doesn't matter. We're going to wind up with a couple terms that could be put together and one that can't be. This situation is analogous to something like this. Say I had like negative 3x plus 6y minus 12x. Like you've done algebra enough to know that you can put some terms together and some you can't. So in this case, we'll combine the first term and the third term. What will we get? Negative 15 cube roots of 4 plus 6 cube roots of 5. You guys think you can handle this? I had 5 examples. We just did 3, and my spidey sense is telling me I think we're probably good. You guys okay? So again, the idea is simplify everything that you can in the hopes that you'll find some parts and pieces then that you can put back together to clean up. Good. All right.